All right, so I'm on a bit of a roll here. I might as well do the other ones. Just a little walkthrough here. Yeah, when we go through these, it should really help with that problem you have to submit. I'll be marking. But knowing the process for these will help a lot for sure. Okay, so now we just did a series circuit above. So now we want to move to a parallel circuit. And again, we want to stick with Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law, right? So important when it comes to analyzing these circuits that I'm literally going to write it out again here. So Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. Okay. So I first want to list out what we're looking for, right? So we're looking for, we got V naught, so that's V with a little zero there. We don't know what that is. So that's that initial voltage of this battery, okay? And we are looking for V1. We don't know that, so this would be considered V1 here. We are looking for I2, okay? And we're looking for R1, and we're looking for R2. Okay, move that up here a little bit. All right, so how do we begin this? We want to analyze the circuit itself and really just take a look at what they give us. So this is a perfect example here to kind of understand like what a battery does. Okay, so we typically use a water analogy, right? And what I mean by that is like this battery is going to kind of supply the pressure that's going to bring the water up to a higher energy level, if you will. It's going to have more pressure to it, okay? And then that's going to move electrons through this wire here, right? The battery is going to provide the voltage. It also keeps those electrons moving. It gives you that current of electrons that goes around. And what we notice something interesting here, because this is kind of a perfect validation of Kirchhoff's current law. So if we start with, and I'm just going to switch my arrows around here. It can be done either way, but we want to align with electron flow, just because electrons are going to flow from this negative end of the battery all the way through to the positive end there, okay? So it's saying here that I naught is 15 amps, okay? And then now those electrons are going to come up here, they're at 15 amps, right? And they're going to split. So they're going to split either down this path or this path here, okay? And we already see that we split here, and this is going to be 6 amps. So at I1, 6 amps went down here, and we can't create charge, right? So we can't just create electrons out of the blue. It's like whatever we start with here for our current, right? If we split 6 down this path, the remaining is going to split down here, okay? And we see that with a parallel circuit, okay? So current into a junction, right? Think of a fork in the road, is going to equal the current out, okay? So going down this path is 6. So to figure out what that is going to be, this I2, we simply have to take our 15 that we started with, 15 amps, minus our 6.0 amps, and that is going to give us what our I2 is going to be, and that's going to give us our 9 amps for that guy. Okay, so we have effectively found out what our I2 is. Okay, and the same idea applies here. So this current's going to go down here, current's going to go down here, and then all this current rejoins over here, and then we're back at 15, right? So you can think of it as, you know, charge cannot be created nor destroyed, okay? So it's going to, once it splits, and then it rejoins down here, okay? And I like to use this analogy too. Like, think of these as some water slides, right? And this battery is like, you can view it as like the stairs in order for people to get to the top platform where you have these water slides. So you got the first water slide here and the second water slide here, right? And maybe one water slide might be a little more fun, okay? But we're all at the same level here, okay? So we know that going down this water slide over here, notice we got 9 amps going down there, right? It has to do with the resistance here, okay? So if we have more resistance, so if there's more resistance, it's not as fun. It's kind of like a slow water slide, right? But if there's less resistance, that's where most of the people are going to want to go. They want to go on a fast water slide and have a good time. And electricity is no different. They want to go down the path of least resistance, okay? So electricity would really love to see just a wire here, right? It wouldn't be good for us because that's essentially a short circuit. If there was just a wire here, all that current, all 15 amps will just keep going down that path that doesn't have anything on it, and then you literally burn out your circuit. Okay, this would actually catch fire. So we put those resistors in there to actually slow down the current and kind of keep it at like a manageable rate, okay? So that's kind of the idea you can keep in mind. Think of the water slide analogy. We can have a whole bunch of these in a row here. Maybe we had like 5 resistors, right? And the current, what we started with, is going to split down each of these paths, but then rejoin over here. Anyway, I don't want to, again, yap too much here, but here we go. So we found our I2, wonderful. So now let's consider our voltage here. Okay, so back to that analogy. This is kind of like a stairwell or like an elevator bringing you up to the same level. So this is going to bring up those electrons to the same energy level up here, okay? Or if you're thinking about people, right, you got a stairwell that brings you to the top level where these water slides are located, okay? So if these electrons are all at the same level and there's these 2 water slides beside each other, right? As you go down each one of these, you're going to be at the same energy level drop than what you originally gained, okay? Because this is all in parallel. So in other words, if this is our V2 here, this is 1.2 times 10 to the 2. That's just, we can put that in kind of regular numbers here instead of scientific notation. That's at 120 volts, okay? So if this is at 120 volts over here, that means that this battery brought all those electrons up to 120 volts at the beginning, okay? Because these water slides, right, these lines here they're essentially at the same level, okay? So that means that this V1 also has to be 120, and this V naught here also has to be 120, okay? And this is what happens with a parallel circuit here, okay? So hopefully that analogy helps a little bit. And that is kind of validation of Kirchhoff's voltage law here, okay? Because ultimately we need to be at kind of 0 volts over here. Otherwise, we're saying that energy can be created or destroyed. But we know energy cannot be created or destroyed. So if we had these electrons up to this energy level, 120, right? We're going to go 120 down these, and then we'll be at 0 here. Okay, and then the thing will just completely go through until the battery burns out, okay? So we know what V naught is. That's going to be 120 now. We know what V1 is. It's going to be 120, okay, because we have these resistors in parallel with the battery, okay? Now we're going to do R1 and R2. And again, like I mentioned before, we want to spam Ohm's law because we have our V1, we have our I1, we have our V2, and we have our I2. So why don't we use our Ohm's law? Super helpful, okay? So let's do our Ohm's law here. So we can say V1 is equal to, we got our I1, R1, and we want to figure out our resistance of this first load and then the second load here. Okay, so I'm going to divide by I1 on both sides. Okay, so R1 is going to be V1 over R1, And we got our V1. So our V1 is going to be, well, it's just going to be that 120 there. And then over our current, so it's our 6.0. Okay, so that's going to be our amps here. And our R1 is going to be, so we're looking at 20 ohms for that guy. Okay. So we said 120 divided by 6, we got 20 there. Okay. And again, getting into sig figs for this, significant figures. Like, excuse me, I feel myself about to cough. So we've got 120 divided by 6.0. If you wanted this in the right amount of sig figs, again, I didn't teach you this yet, but we can put a little decimal right there, and that would be 20 ohms. Okay. And again, we'll go over that when we get to kinematics as well. I'm fine with if you just put 20 for that. Okay, so we got 20 for our R1. Cool. Now we got to do our R2. Let's do our R2 here. So we can do R2 is going to be equal to V2 over I2. And again, we're looking at 120. That's going to be over the I2. That's going to be over 9. Remember how I said this is probably going to be a more fun water slide here. We got 120 divided by 9, so this is going to give us, we have 13 ohms. Okay, and it checks out here. It checks out that this would be 13 ohms. Okay, because remember I said this is the water slide that's more fun. There's literally less resistance going down this path than over here, and it makes sense that most of the electrons are going to want to go down this path, right? Because you can view it as it being a lot more fun for them, right? They're going to be going faster. Okay, and we could see that because 13 ohms is less resistance than 20. Okay, so that is the idea behind it. Okay, again, hopefully this is not getting too long here. Might be actually shorter than the first one. Let's take a look at some of the results that we have here. Okay, so we said 120, so let's take a look. Okay, so we're perfect here. If you see it in scientific notation, right, so our V naught, right, 1.2 times 10 to the 2 volts, that's just the same as 120, right? Same thing here. V1 is 120. We got our I2, that's 9 amps. We got our R1, that's going to be 20 ohms. And we have our R2, and that's going to be 13 ohms. So that's how you solve a simple parallel circuit, right? Remember, use your Ohm's law, use Kirchhoff's current law, the junction rule, right? Current in has to equal current out, and use your Kirchhoff's voltage law, right? Anytime you deal with a closed loop here, you're gonna have the same voltage drops as the total sum there. So in simpler words, right, whatever you start with here, okay, and you go over the load here and over here, right, you're gonna end up at 0, and that has to do with law of conservation of energy. Okay, anyway, if you have questions, of course, please reach out. All the best.